maximum level speed, check there was, we wanted a horsepower of 302, but later on we agreed on 362. So this condition is satisfied. Okay, where did we satisfy the range? Was it in the wing area, horsepower, or the weight of the aircraft, total weight? Total weight, yes. When we calculated W naught and we calculated the amount of fuel, it was based on a range of 1200. Where did we check the ceiling? Well, I will answer that. We didn't satisfy the ceiling anywhere. We didn't make sure the aircraft will go up to 25,000 feet. Okay, we selected the engine to give us maximum power up to 20,000 feet with the hope that with the reduction of horsepower up to 25, it will still generate some considerable power. So we will check that later on. This condition we didn't completely check, although we could have, but we decided on it wasn't really, it will probably not be critical, just like the stall speed. Okay, rate of climb, we satisfied this condition when we looked at the horsepower. It was the critical condition in the horsepower, which required 362. Stall speed, we satisfied it when we calculated the wing area. We calculated the wing area of 170 something to get this stall speed. Landing distance, we checked it when we were calculating the wing area as well. It wasn't as critical as the stall speed, but we ensured that it will be satisfied. And finally, the takeoff distance, we checked this when we calculated the horsepower. The takeoff distance required a horsepower of 118, I think. The maximum level speed required 303. Rate of climb required 362. So this was the one that was critical. So we almost satisfy all of them. So now we have to take the numbers that was generated and get something like this out of them. So it will not help your client if you go and tell him the horsepower to weight ratio is so and so, the wing loading is so and so. No, what he worries about, what's the span of the wing, how big the aircraft is going to be, what's the length, what's the diameter of the fuselage, what's the height of the tail, where are you going to place the wing, at which distance from the nose, what's the diameter of the propeller, how big the flaps or the ailerons are going to be. In your design, are going to retract the landing gear in the wing, or they will be long and will be retracted in the fuselage. So basically, he wants to know how will the aircraft look like. So the objective of this part number 4, that will take us about 3 lectures or 4, is to find or they come up with some dimension drawing of the aircraft that will reflect all the numbers that we have generated. In doing so, we will make decisions, and these decisions have to be justified. Okay. Mostly we will not be using equations, very few, basically nothing new, nothing, I would say, aerospace engineering. It will be more of an art, fun, common sense, and a little bit of geometry that you had probably in high school. So the part of aerospace engineering was done by calculating the parameters. Now comes the art part, okay, the common sense part, the design, the engineering design part. So we will visit all the major components. We will look at the wing, we will look at the engine, the fuselage, the horizontal tail, propeller, landing gear, and we are going to determine how big they are, what are their dimensions, where are we going to place them with respect to each other. So that's the outline of the configuration, and we will start with the engines, being probably in this design the heaviest component of the aircraft is the engine. So the size of the engine is important because it will tell me, can I put it here in the back or in the front, or maybe I will have 2 engines underneath the wings or attached to the fuselage. So that's a decision that needs to be made. Okay. Now, in this design example that we have choice. We can have a choice of one engine, 362 horsepower, or two engines, 181 or 185 horsepower. So that's because the design requirement gave you the option. It could be one or more. Now, in your design project, there is no option. It has to be a single engine because it's a small engine. I think the powers will be in the order of 120, maybe a little bit more than this. So no aircraft company that produces general aviation aircraft will go and produce its own engine. Basically, they will do the design of the aircraft and then they will purchase the engine because the engine requires totally different capabilities. And the investment in designing and producing a new engine is not worth it if you are going to produce 50, 100, or 200 aircraft. It has to be so many of them. So the trend is you design the aircraft knowing that you will purchase the engine. Okay. No one designs the engine when it comes to this type of design. But of course, if it's a novel aircraft, no engines will give me the requirement, then that's a different issue. So people will collaborate with an engine manufacturer to customize or get a custom designed engine. But if we are looking for a single engine of 362 power, then the team would go and look for the engine manufacturers, different engine manufacturers. You will go to Retex, Textron, whatever engine manufacturer is there. You will do a search of manufacturers, compare prices, compare sizes, compare horsepower, and select an engine. So it selects, it's not design. So in this example, one engine that was selected is the Textron Lycoming 540 piston engine. It has 6 cylinders. So you see 3 in here, 3 in here. It's opposite type cylinders, so they operate horizontally like this. And why it was selected? Because it produced 360 horsepower, very close to what I need. And it gives me this power all the way up to 18,000 feet, very close to the 20,000 feet that I have. Of course, I can go for a bigger engine because you see this is slightly less than the 362. I can go 380, for example, if I will find some engine in the market that gives me 380 or up to 20,000 feet or 25,000 feet, I can go there and pick that one. So it is a decision, but you will have to think, is the 2 horsepower worth to have a bigger engine that produce more than what I need? Because you will not find 362, you'll find 380 or 400. So it will be heavier engine, more expensive engine, or I can live with the 360 with slight modifications. For example, where did we get the 362 number? Which condition? We got it from the condition of the rate of climb. So if I go to rate of climb equation and see if I can make the 362 become 360 with a slight change, let's say in the aspect ratio, instead of 6.7, I can make it 7. That would be good because the 6.7 that we put in there, which we calculated from K, or the assumption of K, if I can change slightly so that I can get these 2 horsepower, that will allow me to use this engine, which is lighter, less expensive than an engine that has 380 horsepower. Okay, so the design issue is not one way, it's not low. No, we got 362, let's pick an engine 362. Well, there is not 362. So you have to maybe tweak the calculations a little bit. And the justification, yes? Question? There was a question? Okay. So once you and your team agree on the engine, and you have to justify why did you pick this engine. So here it is. For this example, we pick this because 360, I can account for the 2 horsepower missing by extending the wing slightly, and that will improve the aerodynamics a little bit. allowing for 360 horsepower. Also for the change in the altitude, I can live with that, because remember the 362 was the rate of climb. But at the cruise altitude of 20,000 feet, we want to satisfy the maximum speed. Over there, in the maximum speed, the required horsepower was only 303. So if this engine is giving me 360 at 18,000 feet, then it will be able to give me 300 at 20,000 feet, because remember the curve goes down with density, so it shouldn't be a problem. I can live with that. So that's one choice. It's not the only choice. I told you, you can get a bigger engine. It will have larger dimensions, and it will weigh more than the 547 pounds of this engine. This engine weighs about 210 or 220 kilograms. You can see the propeller is not drawn. Propeller is not a part of the engine. And in many cases, the manufacturer of the engine is not the manufacturer of the propeller. I always give the example to students, the aircraft engine is like the engine of your car, and the propeller is just like the tires of your car. You can get tires from different manufacturers of the engine manufacturer. They're totally different. Okay. Any questions in the selection of the engine? So you see, no calculations, it's just the selection. You have to justify it. Okay, then comes the question, where are you going to place the engine? Are you going to put it in front, making it a tractor configuration, or you're going to put it in the back, making it a pusher configuration? Or maybe underneath the wing if you go for the choice of two engines. Okay. So we can attach them to the wing if you want. So that brings us to the another decision that the team has to make, tractor versus pusher for this time. Now, if you are designing a jet engine, the decisions are going to be different. You will be asking, am I going to have the engines under the wing or attached to the fuselage, or maybe above the wing? Well, that's an option. In all these cases, the team has to discuss the good things and the bad things and be ready to justify the design, because the decision will affect the performance of the aircraft. So let's start with the location of the engine. What's good and bad about each of these configurations? Let's take it here. Is it better to put the engine in front or in the back? So I need of you some answers. I need right in the chat box. Front, because just one sentence, or back, because just one sentence. And of course, you can say your choice as well. You don't have to write it down. You can just unmute yourself and give us your answer.
Doctor,
Mm-hmm.
I think in the back, to balance the center of gravity, to make it in the middle.
In the back, to balance the center of gravity on in the middle. Why would you think in the back would balance the CG?
Because the pilot will sit forward.
So you are comparing between the pilot and the engine, but also there is the wing, right? And there is the tail, there is the structure, there is the landing gear. So let's put it this way. If you put the engine in the back, that will move the CG aft, right? The CG will be a little bit behind. If you put it in front, the CG will be a little bit forward because of all the components. So we are comparing whether we want the CG forward or we want the CG aft. Okay. Now, from this point of view, the forward position would be better. because if you remember what you had in stability in AE220, if you have taken AE20, or as we're gonna explain it when we check stability, it's always more safe to have the CG forward, because instability of the aircraft occurs when the CG starts moving aft beyond a certain point, called the neutral point. If this happens, the aircraft will be unstable. But if the CG is forward of this neutral point, the aircraft is safe and stable. The more forward, the more stable the aircraft is going to be. Okay, so from a stability point of view, a forward engine is better than an aft engine because it brings the CG forward. Okay, so that's definitely a consideration. What else? What else you have to worry about when you talk about placement of the engine, whether it's front or the back? Remember, the engine is going to be attached to the propeller. Yes, Sultan?
Can we relate it to the airflow?
Airflow. So if you have the propeller in the front, what will happen? It will be good for the propeller because it's seeing the undisturbed free stream. But it will be bad for the aircraft because the increased speed of the flow due to the propeller accelerating the air, this will increase the speed on the surface and thus increasing the drag a little bit. Whereas if you have the propeller in the back, that will be good for the wing. It sees the free stream in here, but the flow will slightly be disturbed for the propeller because it will be affected by the existence of the whole aircraft. So again, that's a good thing and bad thing. Okay, each one of them has good thing and bad thing. It's not like all good or all bad. What else? So that's another factor. What else do you have? What about the noise? Would the aircraft be more noisy if the engine is in front or if it's in the back? Well, it turns out to be less noisy if it's in the back, because think of it, noise just propagates in air, and since the aircraft is moving forward, then the noise is not going to be propagated that much. A backward engine will produce less noise than a forward engine. Okay, so from noise point of view, this one is also important. One last consideration is that if you have a forward engine in here, then the air going around the fuselage, you should reduce the separation as much. And to reduce separation, that's why we have this tail cone. Have you ever asked yourself, why do we have a tail cone in the aircraft? The tail cone is just to make the fuselage looks like an airfoil. So why does the airfoil has a tail cone like this? Because you don't want the air to separate very early. You want the air to separate here, not here. So that's why you are going to have a long tail cone, just like this aircraft. Whereas if you have the propeller here and the engine here in the back, this will improve the pressure gradient in the back. We will not need that thing. We are not worried about the separation of the air on the trailing section. So most aircraft that have had a tractor, a pusher type, you will see they don't have the very long tail cone. Just put the propeller and end the fuselage in here. So these are all factors and they are contradictory, but it's up to the team to decide which one is the most important for our design. So these are the good things and the bad things that we agreed upon for the tractor and the pusher configuration. And it was decided, since this engine is big, huge, heavy, 220 kilograms, it will considerably affect the CG if we put it back. So the stability consideration prevailed all above the other ones. And it was decided to put the engine in front, making the aircraft a tractor type, just like this one, not a pusher type like this. So you see, we haven't written a single equation. We have just discussed the options, the alternatives, and came up with a decision. And that's what a design team should do when it comes to decisions. So when you make your report, don't try to say we pick this. You have to say we pick this because here are the good things and they were more important than, and you list the bad things. And that's why you will find both types of aircraft flying, because the consideration here is different from here. The most important thing here is different from the most important thing here. Okay. Maybe here it was weight, so I need a small tail. Maybe here I didn't want a propeller in the front that will obstruct the view of the pilot. Here it was not a big deal because he's a professional pilot. Maybe that was a military aircraft, but here this is a home-built aircraft. I don't want the pilot's view to be obstructed. Let's put the engine in the back. So all these are considerations for choosing the location of the engine. Okay. So we agreed on the size of the engine, the type of the engine, location of the engine. We will do the propeller, but maybe next time. Today we are going to move our attention to the wing. Before I go to the wing, let me see if you have any questions on the choices we have made for the engine.
Doctor, for the engine,
yes,
in aircrafts, especially propeller, do they care about cooling the engine?
Yes, actually that's a factor. That's a very good factor about cooling the engine, because if, for example, if you're talking about a tractor type engine, the slipstream air coming from the propeller will help, of course, to improve the efficiency of cooling of the engine. Yes, that's one advantage of tractor type aircraft. Okay, because you can have an engine that's air cooled, which will be lighter than an engine that's oil cooled, because you are not going to have the oil system. So yes, we care. That's something that we worry about. And one good thing about this engine that's chosen is that it's air cooled. So it would be better to put it in front as well. Yes, that's another factor. Okay. Any other question on the engines? Okay. Now for the wings, we have to draw them. Right now, what we know about the wing is the wing area and the aspect ratio only, which are not enough to draw the wing. You need to have a shape. Well, actually, they would be enough if the wing is a rectangle. If I know the wing area and the aspect ratio, what did we say? The wing area was what? 175 or something. The aspect ratio 7. Okay. So 175. Times 7. So if it's a rectangular wing, the span of the wing will be about 35. Okay, I'm using 175. Is it 175? Yeah, I think I'm just using from. No, it was 176. It was 176. So the span would be 35. Okay, so we can draw rectangular, but do we really need rectangular wing? Don't we need like to taper the wing a little bit? And we said taper is good because it will give me a wing that has a lift distribution close to the elliptic wing, right? And from a structural point of view, it would be better to have a tapered wing. We don't need that much of a structure on the outside. So how do we pick the taper ratio? This is one question we need to answer. Also, are we going to sweep the wing? That means is there going to be an angle between the leading edge and the normal to the center line of the aircraft? We answered the question of picking 2 airfoils or 1 airfoil. And in this example, we picked 2 airfoils. And we got the average of both. Remember, we needed a thicker airfoil in the center so that we can retract the landing gear and put the fuel tank. And we took a thinner airfoil toward the tip. Also, is there going to be any twist in the wing? Just like the propeller, we can twist the wing, changing the angle of attack between the root and the tip sections. Sometimes this gives me important aircraft handling qualities. I would find this even more important in your design project than this example, because it will affect the way the lift distribution exists on the aircraft. So to make choices, we have to understand the consequences of each choice. Let's look at the taper ratio, for example. If I choose a taper ratio of 1, remember the taper ratio is the ratio between the chord at the tip and the chord at the root. If they are the same, that means a rectangular wing, then the ratio is 1. If the wing tapers all the way to 0 chord at the tip, the taper ratio is going to be 0. And in between, maybe we have a taper ratio of 0.5 or 0.6 or 0.4. It turns out that the difference between wings with different taper ratio would be in the shape of the lift distribution on them. So if I have a rectangular wing, I will have the upper curve. If I have a tipped wing, sort of a delta wing, it will be that curve, almost linear. Now, which one is good and which one is bad? Well, our reference here is the elliptic wing. We try to have a wing that gives me a lift distribution that's close to the elliptic lift distribution, which you had in 220 to be the best. So it turns out to get the one that's close to the elliptic lift distribution, which is the dotted line here, I can get this or close to this if I use a taper ratio of about 0.5. And the reason for this, because the separated flow area will be confined to somewhere in the middle of the wing. So what do we make out of this? It turns out that most low subsonic aircraft, to meet subsonic aircraft, will have a tapered wing of about 0.5. If you look at the Beechcraft aircraft that sometimes take off from the airbase on our backyard, you will see it has a tapered wing, and you can almost see, you can judge that this distance over that distance is about 1.5. Almost all. Have a look at most of the tapered Cessna aircraft. Taper should be 0.5. Okay, so that's like a sort of agreed upon value that we will use. So if we know the taper ratio, 0.5, if we know the aspect ratio, and we have the wing area, I can now get the dimensions of the wing. How? Well, the wing is a trapezoid. If I know the total area of the trapezoid, this one plus this one over 2 multiplied by the distance. And if I know the ratio is 1/2, that means this distance is half that distance. I can use simple geometry. This is high school geometry in order to find what are the dimensions. It's an exercise that can take me just 2 or 3 minutes to derive. So this is the total area of the wing. Actually, this is half the area because this is 1/2 of the wing. It's the average base multiplied by the length. Average base multiplied by the length. Remember, here we know the area. I know the span because I know the aspect ratio. And the span square is the aspect ratio multiplied by the area. So I know the B. And if I take the CR as a common factor, CT over CR will be lambda. So very simple derivation, basically from geometry. So I can use the final answer here. The chord root is equal to twice the wing area, which I know, 176, divided by 1 plus the taper ratio, that's 1.5, and the span is 35. So I know now that the root chord is going to be 6.6 feet, a little bit more than 2 meters. And since the taper ratio is 0.5, that means this chord here is going to be half that one. So it was going to be 3.3 feet. So it's going to be half times 6.6, 3.3 feet. So now I have drawn the wing. I know this chord 6.6, this chord 3.3, this distance half the 35, so it's 17. And I know the airfoil here and I know the airfoil here. In fact, I can draw into SolidWorks and draw this wing in 3D. I know everything about it right now. Okay. Any questions in the wing? Of course, I don't know how would the wing look like from the inside. How many stringers, how many spars, how I'm going to design, but that's not the configuration layout that I have. We're siding the aircraft from the outside so that I can check performance. Inside here, that's comes the preliminary design, and that's a step after we finalize the design. not now. Okay. Now, although I can draw the wing, there are still a few things that need to be done. We haven't agreed, for example, are we going to put the wing? That means it's, or will it be a middle wing, or it will be a low wing? So that's another decision that we are going to make. Are we going to have a winglet here on the tip, or an end plate, or not? Are we going to have a fillet of the wing with the fuselage or not? Okay, so we still haven't completely finished the wing. We still have to do a few things. But since we have determined the dimensions of the wing, maybe it would be a good time to get an important value, just like we got the aspect ratio while we were calculating the induced drag. It's important now to determine the chords that we use in the aircraft. What do I mean by this? When you say the wing area S has a certain value, we know it's the planform area. It is this area, of course, multiplied by 2 because of the other half. But when I say Cm, the coefficient of moment, is equal to the moment divided by 1/2 rho v square SC, what is C? What is C in the definition of the moment coefficient? The definition of moment coefficient is M, moment, divided by Q, or 1/2 rho v square, S, which is the wing area, C. What is C?
Chord length.
Okay, can you give me the number of the chord length of this wing?
Is it 17.64?
No, 17 is the span, half the span. That's the span. I'm looking at the wing from the top here.
It's not uniform.
Yeah, I'm looking at the wing from the top. What you see here is half the span. The chord is this length. The airfoil goes in here, and there is another airfoil goes in here, a third here. There is an airfoil, and you can see the chord is not equal, right? The chord changes. So when I ask you, I need to put in my equation C. You will give me C as what? It's not uniform, right? So is it this one or that one? Should we take the average? What we will do? Okay, so people agreed that whenever we say the chord of the wing, we mean the mean aerodynamic chord. By the mean aerodynamic chord, we say, hey, this is a trapezoidal wing. If that was a trapezoid, the centroid of the trapezoid will not be exactly in the middle. It will be slightly here, a little bit to the left, right? So if this is the location of the centroid of this trapezoid, the chord at this location is what we call the mean aerodynamic chord. It will be the C that we use. Okay, so the mean aerodynamic chord, and short named MAC, mean aerodynamic chord, is the chord at the centroid of the trapezoidal area that we have. So I have to find where is the centroid of this trapezoid. That means what's the distance y, and at this y, what is the chord, and that would be C. And in all your calculations in stability, aerodynamics, whenever you want a C of this aircraft, you will take that chord, not the average, because the average is the chord exactly in the middle. If this is a trapezoid, the centroid is not in the middle, it's slightly shifted to the left. So rather than deriving it, I can refer to any of your math textbooks or mechanics textbooks in which you calculated the centroid of many areas. I know you did that so many times, either in high school or in the prep year as well. So you can find that the centroid of a trapezoid, I don't have to derive it. Well, here is the derivation again if you want. The centroid of the trapezoid is equal to B over 6, where B is the distance, 2 multiplied by the taper ratio. I have the taper ratio, I have the B, I can get the location of the centroid. So Y bar is the location of the centroid. The chord at this location I can find knowing the chord here and here. Okay, so here is the chord calculated knowing the root chord and the tip chord or the taper ratio. So again, it's equal to lambda which lambda here is the 0.5, the taper ratio, and the root chord, which is 6.6. So if I do so, I will find that this mean aerodynamic chord is 5.17 in here, and it is at a location 7.84. That point is very important. That chord is very important because it is the chord of the wing. Whenever I say the aerodynamic center of the whole wing, it will be the 1/4 point of that wing. So it will be here. That's the aerodynamic center of the whole wing, not the root section, not the tip section. Okay. Now, what you see here and all these extra lines, it was like an old way to calculate the location of the mean aerodynamic chord. People, rather than calculating, we can draw it in graphically. So you don't need to worry about this because no one uses this anymore. It's just like a graphical way. Here is C tip, put C root. Here is C root, put C tip, connect. The intersection with the center line gives you the location of the centroid. It's more of a graphical way to find centroid of a trapezoid. But since we have the equation for that, I really don't have to worry about a graphical way of doing things. Okay. So I can draw the wing now. I only have to answer a few questions. Where's the wing is going to be, high, mid, or low? Okay. And for this, we will need a little bit discussion, just like the discussion we had on the engine, because each one of them will have good things and bad things. So for this, I will wait until we meet, inshallah, on Monday. So you might read that a little bit and you can be ready for the discussion. I'd rather use the remaining couple of minutes to see if you have any questions, either today or for your projects or the quiz. When is the due date for the progress report? Just want to make sure everyone is aware of the timing. Wednesday. The progress report is next Wednesday. It's 1 week from today, right?
Yes.
Okay. So I hope you're working. I hope you did good progress in steps 1, 2, hopefully 3, and you can follow us now on step number 4. Okay, so that you can produce a good progress report by Wednesday, inshallah. Okay, so next time we will finalize the location of the wing and we will move on to the remaining items. The remaining items were the fuselage, so we will determine how the fuselage is, length and diameter. We will look at the CG, and maybe by Wednesday we will start looking at the tail and the propeller sizing and the landing gear. So hopefully within 3 sessions, we will be able to get this drawing. Right now, we have achieved only this dimension, the span, and the wing dimensions that we have in here. Okay. And we agreed that it's going to be a tractor type. Any questions, Ishmael? Okay, so we'll meet inshallah on Monday. If you have any questions on the quiz, please put them on the group so that everyone will benefit from your question and responding individually to help. If your colleague has the same question, he can get the answer on the group. Okay. Thank you, Ishmael.